Green's theorem allows for many useful conversions between line and area integrals. The original Green's theorem is for regions without holes. However, we want to know what happens in a case with holes. The theorem tells us that if we have a piecewise smooth, positively oriented, simple closed curve in a plane, the following equations are equal. We have the line integral over contour C of f dr equals the line integral over contour C of m dx plus n dy, which is also equivalent to the double integral over the enclosed area D of the partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. It turns out that Green's theorem can be extended with no changes to cover cases of areas with arbitrarily finite holes. Let's try an example of this. We are given the line integral of the quantity natural log of x minus y cubed over 75 dx plus the quantity x cubed over 75 plus the natural log of y dy. We can consider the first quantity, which will integrate with respect to x, to be m, and the second quantity, which will integrate with respect to y, to be n. According to Green's theorem, this is equivalent to the double integral over the closed region D of the quantity n sub x minus m sub y dA. Taking the partial derivative and plugging in, we obtain the double integral of the quantity x squared over 25 plus y squared over 25 dA. We can take the 1 over 25 out for convenience, and rewrite the integral as 1/25 times the double integral over the closed region D of the quantity x squared plus y squared dA. Now let's integrate over the region D. In this case, D is the annulus given by the polar inequalities A is less than or equal to r, which is less than or equal to 5, and 0 is less than or equal to theta, which is less than or equal to 2 pi. We now need to convert our simplified integral into polar coordinates and put in the appropriate limits. This gives us 1/25 times the integral from 0 to 2 pi of the integral from a to 5 of r cubed dr d theta. Now we can integrate with respect to r. After integrating with respect to r and factoring out 1/4, the integral becomes 1 over 100 times the integral from 0 to 2 pi of 625 minus a to the fourth d theta. Finally, completing the integral results in pi over 50 times the quantity 625 minus a to the fourth power.